Yeah. So basically, people lied to me because they told me like they will not be bringing slides, and every presenter, like speaker here, had slides. So I just spent the last 60 minutes doing this, and now I have slides. All right. So this is how we represent the address on the node. Like this is what communication is using, and the idea here is that you have your host, your UDP port, and the key that identifies your node within the network. And that, unfortunately, is a lie, at least for now, because this is how it really looks like. We generate some UI ID, and for it, we use it as a part of that identification here. Now, how the communications will change over time, I hopefully will speak at the end of this presentation. But for now, just stay with me that still that name, even though it's randomly generated as UUID, identifies the node within the network. So we had node discovery. So that we have the peer-to-peer network, and the peer-to-peer network is implemented with Kademlia. And obviously, like if you have to do your slides within like 30 minutes, you can use Wikipedia for your slides. So, like, if you guys gonna ask me how Kademlia works, I don't know yet, because I didn't have to really know up till this point, because Chris sort of implemented the whole thing and it was working. So hooray! So what's the point? But unfortunately. Maybe fortunately, there will be some changes that will be done within how the COM works. So I'm at the moment reading about Kademlia. But if people are interested in the paper, it's available online. In general, they have this little tree here that they hold information about nodes, and that tree has some specific capabilities, which makes it all performant and whatnot. But we are not really focusing on this. We just sort of believe that it works. And Kademlia needs a transport layer for it to work. Within the paper, there are some messages that are being sent between the nodes. We are not implementing the whole specification. We are only implementing the ping and the find node. So ping allows us to, well, ping other nodes, while the find node makes a lookup for the list of nodes that we might not be aware of yet. And oh crap! So you guys probably don't see anything here. That's not good. Is there a way to switch out those lights over here? Probably not. It's a screenshot. Yeah, whatever. I mean, I can use this. Do you guys see it? Yeah. Right now? All right. So, Proto. Yep. So this is how we are representing this, the Kademlia protocol. I can make it a little bit bigger, using protobufs. So you will see that we have this ping and pong as a response. We have a lookup. So lookup corresponds to that find message that you can find in the paper, and lookup response is obviously a response to that. And then we have this. So this last message called protocol, this guy. So it has all those other previous messages. So ping, pong, lookup, response, and well, another one disconnect when we want to disconnect from the network. And that sort of is only Kademlia specific at this point. When we are sending messages, this was designed in a way that it could be sending any kind of messages, not necessarily what we need. It could be just designed like anybody could just take that binary and use it for their own peer-to-peer network. If that was a good choice or not depends. I have my strong opinions about it because this guy is really a pain in terms of code I'm writing. But anyway, anything else that we are sending over this protocol will be closed over this upstream. As you can see, the type is any. So as you can imagine, that might be a pain. But we will see.
Agreed.
Yeah, and it is. But this is how it is. So, as I said, I'm just showing you guys what we have at the moment. We can talk about what we could do about this within communications at the end of whatever my slides are here. So, anyway, I just have to jump back to slide just to remember what I wanted to show you guys. Okay, so yeah, so those slides will work. So this is how Connect will work. So here you have your little node. It might be a bootstrap node, or it might be somebody working in the network already. And you have another node here that would like to connect to this node. Like, how does he know about this node? Well, it can either be a bootstrap node, so he has the address of that running node over here, Or maybe Kademlia working underneath had this node discovery, so this guy will constantly every few seconds ask underlying Kademlia protocol, hey, give me new peers that maybe are available on the network, and if he finds something that is new, he will try to connect to it. And the connection is made in two phases. So the first phase sends this encryption handshake message, which sort of sends the public key of that given node over here. That nice animation, right? That encryption handshake is received by this guy, so now he has a public key of that node that tried to connect to him. So he sends his public key as a response. So now those two guys have the knowledge of the public key of the other party. So now they say there's a second phase of the protocol that kicks in, and that actually sends this protocol handshake message, which for now doesn't have anything at the moment. But what's important is that that message is being framed. What it means that this thing is being encrypted. So once it's being sent over the network here, already this message is being encrypted using this guy's public key. So he can decrypt it, and if he understands the message, he can send the response back, and the nodes consider themselves as being connected. So far, so good. That's the only animation that I have. There's also like one little optimization. So if two nodes used to talk to each other, they exchange public keys, one of them disconnected or whatever, and they try to connect one more time, what will happen is that that node will immediately, like if I know the public key of the other party, I will immediately just jump to the second phase of the protocol and just send encrypted message to that guy. And if I receive the message back, then we're good. And yeah, all right, so Emacs it is. All right, so was that? Probably yes. I have really weird things in my Emacs. So like whenever I save something, Emacs will tell me "good job, way to go" and stuff like that. So you might be surprised. Anyway, well, only because Nash thinks my code sucks that I have to motivate myself. So those are the messages. So those are the messages one more time in protobuf.
Said that.
So as you can guys see, that frameable message here stores protocol handshake and protocol handshake response, because those are being sent as already closed over frame. So now, and yeah, so this is basically here our protocol that we have a disconnect method hello and encryption handshake and encryption handshake response. Those will navigate not encrypted, but everything else within the protocol as it is implemented right now is closed over frame. So if you remember, we had this little upstream here, right, in the Kademlia protocol. This is So those are actually the messages which will be part of the upstream. And yes, each time I have to sort of guess what type it is, and it's a pain. All right, so slides. Okay, so communication has all the needed abstraction about what it means to communicate between nodes is closed over this type class called communication, and there are a few methods. So for example, round trip tries to send a message to a given node with a given timeout and sort of expects a given message back or error. Or you can have ability also to broadcast a message to all of the nodes that you're aware of. You can, for example, this method, find more peers, will run a query to Kademlia asking, are there any new peers that I'm not aware of I would like to try to connect to, and things like, or number of peers available right now. So this is abstraction that we use. And I will show you that abstraction, how it's being implemented in a second. But what I would really like to show you is how, I had slides prepared, so some ugliness is hidden, but now you have to live through the ugliness. So all right. So this is the first. So this is the first phase. Give me a second. There we go. You still see it? So this is the first phase of the protocol. We log some stuff. We fetch the encryption keys. We run some time. We fetch some time counters so we can actually later on push metrics if needed. And then we create an encryption handshake message. We get the remote. We create this protocol node thingy here for our peer. I will tell you what that is in a minute and why is that horrible. But anyway, once we have that message, the encryption handshake message, we use that round trip method from communication to send that message to that node, and we expect a response back. Depending on whether a response exists, yes or no, we either deal with that or we have an error. And once we have that message back, we fetch from it the public key, and we store that public key into our store, and we log that we basically fulfilled the first phase of the protocol. The second phase is pretty straightforward. So the second phase looks like, there we go. So now we expect a message. We expect a message. I'm sorry. We send a message protocol handshake, which is closed over this frame message. So it encrypts it. We send it one more time using this round trip method from communication. The message is being received, and once that we receive that response from our node we try to connect to, we consider ourselves connected, so that we add that remote node to our list of nodes that we already connected. So that final connect method here. Wait a minute, I'm looking for it. So this is basically this for comprehension here. This little guy is actually running the connection. So what we do is that we fetch a counter. We are saying we're connecting to the given peer. We increment the counter on the metrics, fetch the key, and then we do two things. If the key exists, so if we connected to that node in the past, then we can actually run just the second phase protocol. But if we haven't, then we have to go through the full handshake protocol. So full handshake is just the first phase followed by the second phase, while this second phase or full is just second phase with attempt. If the attempt was successful, then we're good. If it wasn't, then we have to go through the full handshake protocol. And that's what it is. Does it make sense? Cool, because it's Scala code, and Scala is ugly. All right, so we done that. All right, so the transport layer. So far, we really haven't seen transport layer running because it was all hidden from us through that type class communication. We don't really see how the internals are implemented, and we see this right now. So the way it's being implemented, it's here. So there's a class called Unicast Network, and it wraps around this ability to send messages over UDP. So we are using UDP, and we're using it here in the Unicast com. So that's crap. Okay. Doesn't matter. Unicast. Where are you? Not this. Unicast. Okay. It's definitely somewhere here. There we go. And yeah, as you can see, it's using UDP. And the question is whether this is good or not. So as you just probably saw in a minute, but I know I was jumping between slides and between screens. But the problem that we're having is that if you look at the API that we are using from the communication, from this abstraction, it's all the time just this round trip method. So even though the underlying transport layer is using UDP, we are sending messages as we would be doing that using TCP. We send a message, and we expect message back. And that's a problem for a number of reasons. If you guys are interested, I can show you what the problems are. The problems that I really painful for me are ones in terms of the runtime and the other ones in terms of implementation. So for example, in terms of runtime, you sometimes, if you run the node, you will see those messages in logs saying a message out of sequence. And that happens for a reason. I send a message to the other node, and I'm expecting the message back within the given timeout. That message never receives within the given timeout, so I give up. I start doing other stuff. But at the same time, that message just arrived. But I wasn't expecting this message anymore. So I'm just logging this. It is out of sequence, right? I'm trying to emulate UDP, with UDP at TCP at this point. And there are other problems. So one of the things that is really killing me is this little guy. So right. So if, for example, if we go to that connect method, which is over here, you will see that when I'm connecting, so the arguments that I'm taking are basically the peer that I'm trying to connect to and the timeout, right? And the peer node is this class, little class here, it's pretty straightforward. Like if we try to class peer node, okay, I don't know what it is. Peer node doesn't exist. I don't know. Should be here. So my syntax aren't working for some reason. But anyway, peer node it's not that peer node. There are other peer nodes in our class. Well, it doesn't matter. Basically, the problem is that sort of this little class is just a structure. It has two things in it: identification and an endpoint, which represents the host and the IP address, and that's all it is. And that's pure. That's just a structure, nothing in it. Really nice to reason about it, comprehend it, test it, whatnot. But you might see that if we have the communication type class here, I'm not actually using that peer node. I'm using something which is called protocol node. And protocol node is created only for the sole reason that we are using UDP, not TCP. So because when I'm sending a message to some other node, I'm expecting from let's say I'm sending a handshake message, I'm expecting response from that node. But I also need to know whether this is actually response for the message that I've sent. Maybe this is something different. Maybe this is something out of order. Maybe this is something out of sync. Maybe this is a very old message. So protocol com. There you go. So protocol node extends peer node, and then so this is already broken by definition, because if peer node is a case class, is a structure, and then you extend the case class, and it's like equals method will fail and hash methods will fail, but it's already broken by design. But the problems are like here, which are killing me in terms of testability and immutability. So we have this little imperative function var. There's a sequence that's being incremented every time you call it, so that I know if I send that message and I receive the message back, and the timeouts are sort of similar. This is the response for the message that I sent, and it's leaking in every sort of abstraction. So if we go to that proto, yep. Yeah, messages carry sequence numbers and timestamps. And yeah, I can actually show you that. So this is it. So whenever I send a message, it sort of has, if that message represents a response, it will have two things. So every message has a header, but also it has a return header. So that if I receive a message here with some given header, I will send you a message back as a response, where that return header will have some information from the header I received you from. So you can do the equation and see whether the sequence numbers match and timestamps match and all that. And this is like, I don't want to go into details, but this is sort of killing me. Like the number of abstractions that had to be built to sort of deal with that was, well, it's just too much, and yeah, I don't like it. So where are my slides? That's it. That's that. Well, yeah. Okay, so what's next? So I hope at this point Nash will take over, but yeah, yes, because I'm dehydrated, and yeah, without water, anyway, so what are we thinking is there are basically two things. Like first of all, we try to implement encryption, and there are so many ways that you can break it. So instead of doing that, maybe we could use something which is robust and it's been here for like 25 years so far. So we're considering using TLS. So if we go, so the first motivation that we have is just go from UDP to TCP, because this is what Nash pointed out, that for now we're just sending very small messages. But once we start sending something bigger, then if you start sending something bigger in terms of those little packets close with UDP packets, that's also a pain, because now you have to keep the synchronization of the packets and all that, basically re-implementing TCP at this point without back pressure. So yeah, so maybe instead of running TCP, UDP, let's go to TCP implementation. And one of those approaches that we could use would be just to use gRPC services, which gives us this little TCP implementation underneath. I don't really have to deal with all the craziness that I'm doing within that code that I haven't really showed you. And we have one cool thing for free, and that is TLS. And that means that we wouldn't really have to do the two-phase of the handshake protocol, where the first time we exchange messages, only we would have to do the second phase of the protocol, because already every message that would be sent over the protocol will be encrypted from the beginning. Now, if that's a good idea, that sort of depends. So there are technical issues, like we are trying to discover whether this is possible to retrieve from the gRPC API the certificate of the other node. Like, this is apparently doable right now on the server side. It's hard for whatever reasons to be done on it. Technically, it's possible, right? The question is whether gRPC and not really gRPC, whether the IONETI is giving that API for us as users, or do we have to, fork IONETI and dig through the code and just find it somewhere out there. The other problem that was pointed out to me yesterday, and we didn't really have time to talk about it, is that the public key from the certificate has, I think there were some requirements about what kind of cryptographical algorithm we're going to use, and whether this is supported by TLS or not. So I'm not really sure if that's the case. Because
Mike says it is.
It is supported, or
yeah.
Okay.
I think that's an excellent question, though, right? Like it would be ideal if the wallet keys for a validator and the TLS certificate use the same set of keys. That way, we can identify the validator by its TLS negotiation. Say, oh, I know who you are because I see that you're using the public key associated with this wallet. Yeah. If that's not the case, at least we can use TLS to get transport security, and then we can do a handoff of key material. But that's
also what I don't know, and this is what Chris was pointing out, that how many connections going to be there, like how many connections, TCP connections, I have to open for a given node if I'm using TCP, right? That's maybe this is something that we should do, like a proof of concept.
Depends on how many calls you're making simultaneously, right? So,
yeah.
So one of the nice things about gRPC is that it does connection pooling and connection management for you invisibly, right? So if you're sending a lot of messages to another peer, and it'll open up multiple connections to allow you to make multiple, RPC calls at the same time. In general, validators are going to have a lot of open connections, right? Read-only nodes can have many fewer open connections because they only need to connect to a couple of validators to get the data feed and make sure that they're getting a reasonably up-to-date copy of the blockchain from one or two validators, and then they can look and, to make sure they have everything that way.
Sure.
But in most regions, that we're going to want there to be as close to full graph interconnectivity as possible, right? That makes the network lower latency. In situations where you can, like in regions where you can accept higher latency, you can have lower interconnectedness rate percentages for the validator set, but the network gets slower when you do that.
Yeah. So, but basically, right now there are two problems we had to struggle with, and I think those are separate. So one of them is the UDP versus TCP. That's one thing, because we could still use gRPC if the TLS is a problem. And so that's one thing, just going from UDP to TCP. But so right now so the problems that we are sort of facing is that Kademlia is a little bit tightly coupled to the underlying transport protocol. So we would like to decouple that using FP. So just Kademlia can instead of being a effectful thing, could just return an effect, and then we have this clear boundary between the transport layer and the algorithm that is responsible for node discovery. So that's one thing. And the other, if that is working, it can be working in gRPC. We can then also, we are struggling right now whether we are able to receive a certificate on the client side from the server side. It's definitely doable in Go. But I don't know if that's actually, I shouldn't really say it. Because now somebody will shout, let's write it in Go, and I'll be just leaving now. You will see me. You will never see me write stuff in Go.
Never write it in Go.
Yeah. So, yeah, that's all from my part. I don't know if you have anything to add.
Well, let's see if we have any questions. Does anybody have any questions at this point?
So the TLS question.
Hold on. Wait, is there a mic?
Yeah. Thank you. So for TLS question, then you'll be relying on third party to verify your certificates?
We don't have to.
No, yeah, we don't need certificate validation, right? We just, like, they can be self-signed and that's enough. The point of TLS is to mostly to prevent man-in-the-middle attacks, make sure that we know who we're connected to, not to guarantee that you know the identity of what you're connected to.
Okay. So if your transactions are already, encrypted or verified using your blocks, what you're going to transfer the messages, right? They are already signed messages. Do you really need TLS?
No, that's the other way around. Like, it's already done. But okay, so when I was trying to sort of discover what can be done with TLS, I found this really cool YouTube video. I can share it on Discord. When the guy who was spent the last 20 years implementing TLS was showing how TLS was attacked and how many different ways, how that little simple protocol of just exchanging public keys can be sort of exploited. So the idea here is, why create our own encryption handshake protocol if we can reuse existing one? So that's the main idea here.
I think I understand, but why do you really need to handshake encryption protocol, right? I mean, your messages are already
so that will be deleted.
Signed messages.
Oh, it's signed message.
Yeah, I mean,
you have to know what node you're talking to. So when you go to connect to another validator, right, you have to know who it is. They have to send you. You have to receive their keys so that you know which of the validators on the list you're actually talking to.
I think the question was why we encrypt messages other than just sending a signature.
So
right?
The way I see that, the COM layer should be dumb, completely a dumb pipe. It should. That's where consensus comes into picture. I think those kind of things should take care of your messages, how messages are valid or not, because that's anyway you're going to build when you're sending messages from one node to another node. So personally, the way I see the COM layer should just pass the messages, and upper layer, at the abstraction from COM layer, should take care of the rest of the things. The message signing, signature, or encryption algorithm, and that sort of thing.
Cool. Any other questions?
All right.
You nailed it all, Pawel.
I can dance for you. Yeah, so I will take the opportunity. If there are Scala developers here, and I see some, so I will be doing, after the recap sessions, I'll be doing a little presentation about MTL, tagless final, how that we are using this in COM. I mean, I will be not showing communication. I have another example where I just want to show you guys what are the benefits, and I have some benchmarks running, and I have some open questions for Greg, so if you could come at least for the last end of the presentation. Especially after the benchmarks are shown. So yeah, yeah. Thank you very much.